y'all. This is section 3, Newton's third law of motion and momentum. Newton's third law states, hold on, let me go back and make sure that you are going over the notes repeatedly and reading the book. I'm not putting reading the book on assignments, but you should by now know, this is April now, that you've got to read the chapter. Newton's third law says that a force cannot exist alone. Forces always exist in pairs. So according to Newton's third law of motion, whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. So you've probably heard for every action there's an equal and an opposite reaction. That's what this is. Okay? So action and reaction forces. These two forces are equal in size and opposite in direction, which is what I said. They've got to be, for every action, there's an equal and opposite reaction. So, according to Newton's third law, there must be an equal and opposite reaction force. So, action, reaction forces, and motion. So, for example, swimming. The action-reaction forces propel the swimmer through the water, and then the swimmer pushes against the water. So the water pushes the swimmer ahead. So if I'm doing like freestyle, okay, that's like the crawl stroke. As I pull my hand through the water, I'm pushing the water back, and then the water is propelling me forward. So that's my equal and opposite reaction. Here's the thing though. Action-reaction forces do not cancel, because what you're thinking, okay, well, for every action there's equal and opposite reactions, so they just cancel each other out. No, because the forces act on different objects. So the action force acts on the water, and then the reaction force acts on the swimmer. So I push the water back, and then the water pushes me. If I push on a wall, trying to get it to move, I push on the wall pushes back on me. Okay, I push the wall, then the wall pushes me. So this is the equal and opposite reaction. They do not cancel out because they're acting on different objects. Okay, I know there's some pictures on there, and they talk about this in the book, so it's pretty good. So read that. All right, momentum. This is the next one. This is a new formula for us. Okay, so far in this chapter we have had we talked about the Newton's second law, acceleration equals force over mass, which is also the same force, the same equation as force equals mass times acceleration. And then also weight equals mass times gravity is pretty much the exact same formula too. All right, momentum is the product. Product means something that's multiplied. So the product of an object's mass and its velocity. Okay, an object with a large momentum is hard to stop. Okay, this is why when you start driving, they say be careful of 18-wheelers. Do not pull out in front of them. They cannot stop like a car can because it has so much momentum because of its mass and its velocity. If an 18-wheeler is going 70 on the highway or 60 on the highway with all his cargo, he cannot stop like a car can. So an object has a large momentum if the product of its mass and velocity is large. Okay? So, momentum, this is your new formula, equals mass times velocity. And the way you write momentum is kind of specially P and then equals M times V. So, your momentum is like a special P, and it's kilograms times meters per second. Okay, so there's not a unit for momentum that's like a Newton. It's just momentum. So you're always going to have to say, oh, the momentum is 50 kilograms times meters per second. So there's not a shortcut way of just saying a Newton. Okay, so conservation of momentum. This means that the momentum does not increase or decrease. Just like all the other conservations, that whatever you started with, you've got to end up with the same amount. This is the same thing. So according to the law of conservation of momentum, if no net force acts on the system, then the total momentum of the system does not change. So what this means is like if a car hits another car and not like a third car hits it, the system is one car hitting another, then the momentum that the first car loses, the second car gains. Okay? So in a closed system, that would be like two cars. The loss of momentum of one object equals the gain in momentum of another object is conserved. So the way I talk about this, and first of all, there's a really good train picture in the book that really talks about how it's always the same momentum, but you'll see that one train car is going really fast and one stopped and stuff like that. So let me explain this. Okay, let's say we're in the hall walking at school, okay? And I'm walking behind a student and I'm like hurrying. And the student in front of me is going so slow, okay? And so I accidentally run into the student. When I run into them, I'm going to push them forward. But I'm going to keep moving because that student's also moving. So I'm going to end up pushing that student and then I'm going to slow down a little. So all of my momentum got transferred to her or him, and then some of mine lost the same amount. So whatever I transferred to her, I lost myself. Okay? So let's say that I'm walking down the hall and I'm running or walking really fast, okay? And there's a student who stops right in front of me. You always, like right at their locker or something, okay? And I run into them. Because they're stopped, I'm gonna push them, but I'm gonna stop myself probably, okay? So I'm gonna end up pushing them forward, but I'm probably gonna stop myself. So again, all my momentum got transferred, okay, all to them, and then I lost all my momentum. That's what that means, conserved. The same amount you have momentum between the two of us, but I lost some, she gained some. Okay? All right. So that's it.